So time is up. Welcome to all for joining this webinar about Ki, WPC Ki Introduction. I'm Bernd Olof Hellström, Field Applications Engineer at WPC, the Wireless Power Consortium. And I will guide you through the new standard of kitchens and is what we all want in our homes. The total time we got for this webinar is exactly 1 hour, and during this session, you can use the chat to ask questions. Tim Soinebrink will be supporting there, and while I'm the presenter, keep in mind this is a brief technical introduction, and all in the depth technical information is in the specification. It's only available to members, so all answers may not be possible to give. This presentation contains only open information and will be distributed to all the registered emails after this session. This email will also be recorded. This webinar will also be recorded and therefore all muted in this session. Finally, this presentation is only a brief description of Ki and not the full specification. WPC owns the material and reserves the right to change parts or in whole at any time. So, with that said, the agenda for the webinar, I will say a few words about WPC. Many knows about WPC, but there could be a few in this world who don't. I would also mention the standards we are delivering together with our members. The main topic of today is Ki Introduction to Cordless Kitchen. There is a Q&A all the time in the chat. So use that if you have questions. And we have to strictly be limited to 1 hour in this session. So some about WPC. It was founded in 2008. The WPC is an open standard development organization with a mission to establish and maintain global standards for safety, efficiency, and interoperability of wireless power applications. WPC is a world-leading authority of wireless power transfer and a hallmark of trust relied upon millions of people in countless countries. Nearly 1 billion devices will be shipped with the WPC's widely acclaimed Ki wireless power standard in 2024. Building on the success of Ki, WPC will launch its second major wireless power standard, Ki, later in 2024, bringing the unprecedented inconvenience, safety, and contemporary design of Ki Cordless Kitchen to homes throughout the world. So, becoming a member, some of the benefits of being a member are the access to draft of the specification, to work groups, direct discussion of leading WPC members, a lot of good context for reaching out to the market. You will also have an influence of roadmaps, the commercial requirements, technical choices, voting rights for the new specifications. It gives also shortened and more cost-efficient product development cycle time. You can participate in plug fests to try products in a lab environment. You also have access to early draft specification and test tools to expedite product development. It gives also improved planning and decision making because of the contact to people, key people on the market, and also early access of information. The certification and branding is important so the product can be registered in the certified product database in WPC. You also will have the right to use appropriate WPC logo on the product's packaging and market collateral as proof of certification. So if you want more contact about membership, you should contact Paul Golden. He's a market director at Wireless Power Consortium. You will have his email here. You will also have contacts at a later stage of this presentation. Everything I present today will be sent out, as I said earlier, so you don't have to take notes. So what is all the buzz about Ki? What is Ki? A brief description of Ki: it's a new standard for appliances in our kitchens. It's the convenience to remove power cords. Ki offers better modern design. One appliance will work regardless of the electrical standard in the world. One product will work everywhere. It is safer because water and electricity aren't friends. We all know that. So Ki 1.0 is now, and product will be on the market in 2025. The cooktop can be used as before. So it means that if Ki is implemented in the kitchen, nobody will see it. So how is Ki working? There are no batteries in the device, and therefore no leaking batteries. It's easy to use. Just put the appliance in place, turn it on, and it works as it should be, but without the cord hanging. The appliance is also wirelessly powered from the cooktop, or it's supplied through the induction hob. The appliance is also only powered when it's used on the surface. It turns off when it's removed. What is Ki not? It's not a wireless charging device. The power is available only when the appliance is used. You can't charge a mobile with Ki. It simply do not work. You cannot charge anything else. You can just power things, appliances on the cooktop. So to better tell what Ki is, it's better to watch a video. It's just 30 seconds, so pay attention. This video and a lot more is available on YouTube. Just look for Wireless Power Consortium to get more information. There is also a link on the right side, which I also want you to do is to subscribe to our channel. You will be the first to get updates and we release new material. So go to YouTube, click on subscribe. And here is the video.
The Ki Cordless Kitchen standard is bringing tomorrow's technology to today. Using the Wireless Power Consortium standards, built-in magnetic transmitters deliver up to 2,200 watts of power to appliances wirelessly, with safety and flexibility top of mind. From blenders to food processors and mixers to kettles, the kitchen of the future is upon us. To learn more about Ki, go to wirelesspowerconsortium.com.
So that was a good introduction. In the coming part, the content will be more technical. It is a Ki technical introduction after all. It won't be too heavy and no math formulas. Much technical information and details are there, but it will be more pictures at the end. So the content is divided into two sections: the Ki transmitter and the Ki receiver. The hob, the transmitter, the PTX, as it's also called, will be used as a name, as well as receivers, or PRX, or appliance. These are the same thing. I will talk about how the transmitter communicate with the receiver and back. I will also compare the known induction hob with Ki for the differences. They are not the same, but they can be combined, as you can see on the picture where we have induction hob on the left for a traditional pan, and in the middle there is a combination of induction hob and a blender on Ki. So this spot can be either or. And you can also put Ki transmitter in a cooktop, and this is the concealed version where it's hidden underneath, and you just put it on top and it works where it is. Just a reminder, if you have questions, ask on the chat to Tim and he will respond back. I will start with the system overview and then talk about the structure of a Ki transmitter. So this is a simplified view of a conventional induction hob. this is the transmitter, and it's containing a power converter, and it's delivering the high magnetic field through the coil that is creating eddy current on the surface on the frying pan, for example. The problem here is that there is quite low chance for feedbacks. There are a few exceptions, but the user control is on the user interface on the induction hob, and you have to control yourself to adjust the temperature. Important is user interface is on the hob, which is a difference later. As you all know, milk is known to cheese this feedback loop, and we all know what happens when we look away. So this is not a very good system to control, but it is very efficient to heat up frying pans. The Ki system is different. Here we have basically two channels, the power channel and the NFC channel. This NFC channel had two roles. It communicates on a high speed, but it's also providing power between the transmitter and the cordless power, because remember, we do not have a battery, so we need to provide some power to activate things before we can use it. The NFC provides this energy, but it also provides the data. This is the main difference. Plus, we have now, when it's activated after some authentication, etc., then everything is on the appliance. So the appliance is in charge of the power. So it sets the limits, it sets the level of power that need to be transmitted. So the control is now in the appliance, not in the transmitter, like in the induction hob. So by comparing Ki to induction hob, we can see several clear advantages with Ki. We have, for the induction hob, it's a simple technology and heats up any material with the magnetic permeability, like iron. It doesn't really differentiate between pans and other objects. It's a slow power regulation. We all know the huge mass takes time to heat up, and it's only done by on-off cycling. And the transmitter output is controlled on the transmitter's user interface. In Ki, it's different. We are using NFC communication, and it transfers also the power we require to control the device from the device. Authentication between transmitter and receiver is required to make sure it is an authentic device we are using. The appliance controls the transmitter through the NFC, so it means that everything we adjust on the receiver is sent back to the transmitter to control the power. And it requires continuous and accurate dynamic power control. It's not on-off cycling like induction hob. And it's fast. Power delivery must be started promptly within 60 milliseconds. The transmitter can be designed to support both Ki and traditional pans, as I viewed on the picture earlier. It's an optional feature of having foreign object detection. Any other objects, mobile or kitchenware, are not affected on the cooktop. So, how is the system works? This is a brief picture on the system states. There is a standby state where everything is basically shut off, but it's ready to work. If the appliance get an on-off switch turned on, it's always off when it's put in the place on the transmitter to prevent accidents, and therefore it's essential to turn it off and on again to activate the device. So then it entered the discovery state, where it start to receive power and start to receive, let's say, basic check. So the transmitter understand, oh, it's a device in place and need to communicate and deliver power. Then it is that's the first state, and it's also initiate the device, ask for ID, basically checking if it is authentic device in place. So it's just not anything you bought cheaply. Then you have the connected state. When everything is sorted out between the transmitter and receiver and is ready to use, you can turn the device on now, and this time is very short. It's typically half a second or shorter. We have then the ability to turn on the device or set a user-defined power setting. The blue is the power delivery, and it is indicating how much, let's say, when the power is delivered and when we're communicating with the device. So in between you can see red spots, and that is when we communicate back from the receiver back to the transmitter and do the adjustments. The blue is the power level. So how complicated is the electronics in the transmitter? It is containing a standard single-core microcontroller with NFC receiver and NFC amplifier with protection circuitry. The microcontroller is similar to what's already in the induction hub. Just a few other blocks are additional. It's the NFC reader and also the NFC amplifier with an antenna. It's using zero crossing to create a heartbeat in the system, and from there it's quite similar to induction hub, except for the communication channel. The microcontroller is synchronized with the mains, as I said, and it's generating a kind of heartbeated system. It has an NFC controller. It's in the blue, doing the communication and providing the 200 milliwatts energy through the amplifier to the coil via the filter. Then we have the microcontroller doing all the authentication and the rest of the thing. The rest of the electronics is supporting, so it means that could be part of the rest of the induction hub. This is just a development kit, and therefore there are more electronics there. Just to indicate the size. So it's, generally speaking, it's not much required. So another picture of how it could be implemented. This is the traditional induction hub on the left side. There are two different types of key transmitter defined today, the cooktop and the concealed version. The concealed is hidden in the workbench. The cooktop has, as induction hubs, similar look, and it's hidden under the ceramic glass. This key transmitter can support also induction hubs, so it could support both. Not required, but it could. And it's important then that we have the material in the top that is non-metallic, so it is, let's say, beneficial for the magnetic field to transport through the bench to the appliance. Some about the power levels. We have 3 regions defined in the world. Europe and Asia America, we can provide 220, 240 volt up to about 10 amps and more. So therefore the limit is 2.2 kilowatts. Region 2 we have in North America and Central America, it is 110 volt and 20 amps, therefore it's about 1.6 kilowatts. Region 3 is where we have 110 volt and 15 amps, therefore we have a limit of 1.35 kilowatts. These are just what is possible to get in these regions. I mean, Ki will work anyway. It is just depending how fast it goes. It depends on how much energy is given. So some about the power coils and NFC antennas. There are 2 groups of transmitters, the basic and the general. They are defined depending on the power levels available in that region. So there is a limit of 2.2 kilowatts, which is available as maximum defined today, where we have 220 volt. And then we have the other regions which are below 1.6 kilowatt, which is the basic area. In this picture is 1.35. And the coil size is required, and you can be anywhere in these areas to support. The size of the coils are typically between 8 and 18 centimeters, 21 centimeters for general. And you can see the coils on the side, they're power coils, and you have also a base with more details about that later. So here's a better picture of the transmitter coil. You can see the magnets underneath, which is essential to focusing the magnetic field in the right direction. We have the winding of power wires that delivers the power from the transmitter. The size of this one is typically up to 21 centimeters. The height of this package is about 1 centimeter in total, including the NFC antenna. For US, it's about 3/8 of a quarter. That's 3/8 of an inch. Here's a typical example of NFC antenna. It's especially designed to operate in a strong paramagnetic field because it's on top of the power windings. The wire is a typical Litz design on a base of mica. It's the gray material, which is a flexible silicate material without any ability to absorb energy from the magnetic field. And it's also flexible and reliable over time. It's a traditional and known material. It looks like metal, but it isn't. It's good to know. It's just a color. This is a cross-section of the transmitter, and with the receiver on top is the orange block. And at the bottom you have the purple, which is the power transmitter. In between, in the green, you have the NFC on the transmitter side, underneath the ceramic glass. On top, as I said, you have the receiver with the receiving coil and also the NFC antenna. You can see they are a bit different in the receiver. The receiving coil is at the side. This is just to maintain the good coupling between NFC, less depending on the positioning, and also making sure the power delivery works. There's quite a lot of freedom there in positioning. It's generous in all directions, and it's not limiting the functionality, neither the communication nor the power transmission. It works quite well. You don't need to be that exact to position things. Some about the power control. It's a bit more advanced than induction hobs and requires a selected mode of control, depending on power delivery. So the picture is showing a typical function between voltage equivalent to power, depending on frequency. So you have one peak for the transmitter and one peak for the receiver, and this curve looks different depending on the coupling, and it depends on the positioning and the distance, and it is something that need to be maintained and observed in the regulation, because there are regions in this area where it shouldn't be because it's not efficient, and you need to select if you should be on this frequency or the other one. To do this, you have three means of power control: the frequency control, dynamic duty cycle control, and also phase cutting. So what is that? So the frequency control is basically controlling the frequency. The switching frequency is not the 50 hertz, so it's controlling the frequency to the coils. And also duty cycle control, the same basic frequency, but it's changing the on-off duty cycle. And then we have the third state, which is phase cutting. This is similar to old house dimmers. So you're using just a fraction of the 50 hertz cycle at some level. The last one is used when you have very low power levels. So to show this, I have a video of power delivery, and moving through all 3 stages. Before I start the video, I will explain what we will see on the oscilloscope. The video will show a ramp down and up in power. And the voltage is visible here as a level on the fixed load, receiver load. The first it will view frequency and duty cycle control down to about 100 watt, where we change to duty cycle, and that will be very obvious. And then it goes back from duty cycle via frequency control and last duty cycle to get up in power again. So first, frequency and duty cycle control, lowering the power level dynamically, then we change to phase cutting to reach a lowest level. Then it goes back to in duty cycle of the 50 hertz, and then moving up the frequency and duty cycle to reach full power level again. That was the last video for today, unfortunately. Here we have the functional design to show Ki's capability. It's a full operation functional prototype to show the capability of a concealed or under a wooden countertop. If there are product designer here, I can just say, don't fear the size. It can be designed to be much smaller and thinner. For this design, we have a Philips concealed transmitter prototype. It's based on a half-bridge inverter and an STM controller reference design. As you can see on this side, here's the controller, and here is the inverter section, and here you have the filter. So this is the package in the metal underneath, and it's also using SCF General Concealed TX power coils and NFC antenna. More about that later. That's all about the transmitter. I'm now moving to the receiver. To recap on the system at large, on the right side, there is a controller unit. This is the one doing the master control when it's powered up. We also have a resonant tag for the power, and also some other additional blocks inside the RF control unit. You have the microcontroller plus the NFC reader. The NFC reader has double functionality. As I said before, it's harvesting the power. We added that as a separate block. It's also doing the communication and authentication. Moving into more details, we have the green area on top here, contains the harvesting block of energy. We also have the microcontroller down here. We have the NFC here, and that is where we communicate, get the power, all that things. It's important to keep a track on the power because that is also synchronizing the communication backwards. So it's a lot of things the microcontroller need to do, but it's not comprehensive. It's quite few components. The rest of the area is basically containing what is required to support the functionality in the appliance. There are 2 power profiles defining Ki. The control power 1, which is on the right. It is a simpler device with just a simple load that can be turned on and off. Usually types like water kettle, toaster, waffle makers. And we also have the control 0, which is more advanced, and it can support different loads. You have a power regulator, you have different other things that could be turned on and off, like in fryers when you have a heater as well. This is more advanced electronics and require more electronics, of course. But important for all these kind of things that we deliver a level of required power to the transmitter, because we do not want to get more power than we need, because that is just waste of power and that is generating a lot of heat. So the feedback loop is essential, and it is continuously delivered to the transmitter the level of power required. A typical example of receiver power coils with NFC antennas. On the right side, we have the power coil in brown. It is about 15 centimeters, 6 inches. And also on the outer peripheral ring, we have the white. It is the NFC antenna for the receiver. Underneath, we have the magnets to focusing the magnetic energy where we want it, so we don't spread it all around, because that is just NFC issues. So it's important to have the magnets there, both for the efficiency and for the EMC. This coil package is available from SEF, and we have the contacts at the end of the presentation. So how can the receiver be integrated? Here we have a blender with a motor. It's a gray area, and also we have at the bottom a modified base plate with a coil that is delivering power to the control board with the user interface and some LEDs, could be buzzers, could be a lot more things. And we also connect it to a LED guide. LED guide is a transparent plastic piece that distributes light very well, so we can create more advanced light distribution that way. You also have some mechanical features like air tunnels to cool the device. Motors get hot usually. Important is that we have an indicator, because there is a demand in the specification that we have a kind of feedback of some sort to the user. Here's the picture of a base plate. It's a model modified with a Ki coil. Important here is that the coil is not limiting the design, or it's not the limiting in that sense. It's determined how it should look like. It is quite flexible, and the base plate is usually determined with other respects than the coil, and that gives a certain design freedom. We also have the possibility to have some ventilation vents at the bottom, etc. So this is it gives a good picture of how flexible a design can be. Some about the low voltage conversion, because we are basically grabbing power from two places. One is from the NFC antenna before activation, and during operation, we are taking the power from the power coil. The thing here is that if we need 3.3 or 5 volt or similar, we're taking that directly from high voltage like 200 or 400 volt rectified. It's a challenge, because we need to have a duty cycle, a PWM controller that is about 1% duty cycle. That's a challenge. So it is required to take some serious advanced design considerations when this is implemented. So the power levels required in this system, 2 stages. Harvesting of 200 milliwatt before things are activated. That is what we get. So 5 volt, 40 milliamps roughly. That is available for activation of the unit. It's more than enough. It's proven to work very well. Some people have just a LED to turn off things. Some have used more advanced displays. So the power is there. The NFC is also distributed in the time slots in between the power. It's important, but in these areas there are not much power delivered, because main power is coming from the power grid. At that point we have more than 200 milliwatts available. I forgot to say that interesting how we did implement these kind of things, because the NFC communication is in between. One may say, isn't there a lot of power doing this way? Wouldn't it be better to have the communication on as overlaid on the power waves? It's very noisy and requires a lot of extra filter components. If you do it this way with communication slots, the bit loss is very low, and it's very beneficial to get an increased and robust communication. And it's not much energy you lose in this area anyway. So here is the board used in the blender. I will show in the next picture. There's a low voltage power supply implemented, harvesting for that feature, and also the NFC antenna. We have the matching network for that as well. It's important because it's about 13 megahertz, so you need to consider the frequency and need to have impedance matching there. Philips blender, where this board is used, you can see this is a traditional design. You can see at the bottom you have the coil with the magnets, and on the side inside you have the control board controlling the motor and monitoring the diode. So this is control type 0, and it is more advanced, but still there are a lot of space inside. So DC-DC converters, as I said, sometimes a challenge because it's 1% duty cycle in the pulse width modulation. And that means that we don't have much use of traditional converters out there. It needs to be quite good design to get 1%. Usually DC-DC converters are considering like 50 or 70%. So you need to have a dedicated high voltage converter. There are other options like a passive converter, kind of a capacitive converter where you sacrifice some of the power to be more reactive. Makes it a little bit more easier, but the problem is you have a very limited range of power, and the voltage is very sensitive from that sense. So it need to be considered what kind of solution that is going to be used. Some about the communication and the microcontroller and the user interface elements. The hardware and software is supported by STM reference design. They have the NFC reader in IC. They also have the libraries available. They also have the library for low-level key, which is required as well. They also have some software for use in this kind of application. Some of the typical user interface elements are the buzzer, the LEDs, the indicators for feedback, knobs and dials for you to adjust things. The key specification requires an indication. As I said, you need to have something that gives a feedback. There are prototypes I've seen using buzzers or double beeps or blue-red for indicating power level, etc. So there are freedom there as well. So we have some example of implementations of a water kettle. This is a simplified design with very few components. We have an NFC receiver, which also acts as a controller, or could be used as a controller. There are NFC chip providers in this world who can offer a use of the internal power to control a device like a key kettle. It minimizes the BOM to the extreme minimum, so it will be a single chip solution to do this. This water kettle has just one on-off button, It communicates via the power coil and the NFC antenna. A very simple design, not much, but very useful. So, some about the development capabilities. So we have some good design support from STM. They providing development kits like this one. It's a box, 2 parts, the high voltage part with the coil. And this is the NFC coil, and then there is the power coil. It is the traditional cooktop. Then you have the power part. This board is also seen previously as a design used in cooktops for demonstrations. And also they have a display and some USB connections for connecting to a laptop for control and monitoring error messages, etc., etc. So this is a very useful kit for product development. And I would say this one or the next one is required if you're doing something, because you need to have a solid working transmitter or receiving when you're developing the other side. If you have two sides and you're developing both at the same time, it's a bit of a challenge. So here's the development kit from Defion. We have the development power transmitter, which is looking kind of a cooktop. You have a surface on top of ceramic glass with a Ki logo, and then you have the device under test or development you can put on top and connect to a PC and get control and communicate, generate errors, all that kind of things. And also now they all have developed a development receiver. It is this box you put on top of the transmitter. And it also have a box of supporting electronics. So this one is definitely useful if you are developing a transmitter, or a combination, of course. And both of them are available from Defion soon or at this point. So this is something I strongly recommend to have in possession when you're developing, because otherwise it will be a lot of time, and the money spent on these kind of things will be paid back very, very quickly. So second last slide. Here are some contacts for the products you need in development. I'm also here to support you. I'm on the second last row. Paul can be contacted for marketing things or membership. On the top, we have Defion for the development transmitter and receivers. We have the contact to STM for the reference design and the libraries required to development of the products. They also have a set of application notes which are required. I also say that becoming a full member is also mandatory. Only WPC members can access specification and certification. You need to be a member to certify and receive or use key logotypes on the product. The authentication is also required to get a fully functional and quality device, I would say. And that is only available to key members. So become a member, talk to Paul, and he will support you as much as he can from that perspective. So if you have any questions, I will I will monitor the chat. A team have probably been available for you. I've seen some of the messages popping up. So here is the last slide. You can also contact us with via email if you like, and send suggestions or questions directly to us. And as a reminder, there will also be 4 additional sessions with deep technical material on cooktops and appliance designs. Those are obviously for members only, and then the first one is in this set will be on April 25th. And the other will follow soon after, and some of them in June. So yeah, I'll let you continue with the chat for those who are who need more information. To all others, I say thank you for participating, the first in the series of Ki technical webinars. I hope you enjoyed this session, and I hope to have you back here soon. Thank you, and bye.